Yeah, let's go ahead and get started. Welcome back. I'm glad you're all here. I hope MP number 2 is going well. I think you'll find today and this week and even going into next week very relevant for what you're doing in the lab. The topic is kind of ambiguously called graphics rendering pipeline. The whole class is about the graphics rendering pipeline, but today we're going to be talking about a lot of the fixed functionality in the modern graphics rendering pipeline. Another way to think of it is what is happening in the so-called non-programmable stages. So we're answering effectively 3 questions in this topic. The first is, as we go from our geometry all the way down to our display, given an object that is defined by a set of vertices, how do I fill it with colors? The rasterization issue that you're currently getting through in the lab. Next, how do I determine what to put on the screen? What part of our geometry is actually necessary? What parts can be ignored as irrelevant? And then finally, first thing, what is the actual shape of the object and how do we determine that given an input set of data? I've been using the terms a little bit interchangeably up to this point, and that's still valid from a lot of perspectives, but using the term vertex and geometry as effectively the same thing, that's not strictly true. We specify vertices for our system. These are our points in a 3-dimensional space for which we also specify other attributes for those points. Geometry is the actual geometry. It's the shape of the things that we actually want to render here. It turns out that as long as we restrict the class of transformations we are going to apply to our incoming vertices, the assumptions we can make about the input geometry still hold after those transformations have taken place. You may hear the term affine transformation either when looking at computer graphics related materials or when studying linear algebra. It means that it just preserves the lines. If there's lines in the input geometry, the lines will still be preserved. If there's parallelism in the input geometry, that parallelism will be preserved. Things like lengths don't get preserved, angles don't get preserved. The term affine and linear transformations are sometimes used interchangeably. All linear transformations are affine, not all affine transformations are linear. Visually, if you hear the term, this representation is what you want to think about. So if we limit ourselves to the class of transformations that look roughly like what we're seeing there, in which if we have a quadrilateral with 4 vertices, we apply one or a series of that class of transformations to it, the end result is a different looking quadrilateral. As long as we limit ourselves to that, it doesn't become a hexagon or something like that after we apply that transformation. Then there are a series of assumptions we can make about how we specify our geometry such that vertices and geometry have that kind of one-to-one relationship here. We can do the transformation on a vertex by vertex basis. Once we have done those transformations, we eventually still have to determine, okay, it's not just a set of vertices in isolation. They're corresponding to some polygon, to some shape. We have to actually do something with that. And then at that point, we don't really think of it as individual vertices anymore. Now we think of it as a triangle and what we apply to our triangle. This is a slightly different version of the rendering graphical logical pipeline here. Slightly more helpful in terms of the underlying sub-stages here. I think it'll be easiest for us, even if this is really an architecture class, to focus it from a software perspective in terms of what are the data types that are entering each stage, and maybe the hardware equivalents, as our vertices are sent through here. And we're going to focus on 3 of those stages today, a couple more on Thursday. This is ignoring some things. There's a whole separate pipeline for accessing just pure pixel information. There's the actual buffers at the end of the day, which from our perspective is just regions logically divided in our memory, and none of the display part is here as well. But those are the rest of the stages that correspond on a roughly one-to-one correspondence to the hardware modules that are either provided for you in the graphics pipeline in your hardware, or you are responsible for this week and beyond for building in your hardware pipeline in the lab. So using our very old school fixed function OpenGL, so we're not worrying about what I was talking about last week with your vertex array objects and vertex buffer objects. That's still valid. The end result is still the same. Still a stream of vertices coming in. So some piece of software is specifying a set of vertices. Here we're using the fixed function OpenGL spec. Your lab version of it, which is closer to version 3 of OpenGL, is specifying these buffer objects, but it's the same result. We are specifying here a particular type of primitive referred to as a GL triangle strip, and we're specifying a series of vertices for it. Now, we don't have to be experts in this fixed function OpenGL at all, but I think we can kind of squint our way through it and kind of guess what is happening here. GL clear color, that still exists today, 1, 1, 1, 1. What is our clear color going to be? It's going to be white. Full red, full blue, full green makes white. We're then going to clear the screen. So we set a white background on the screen here. GL load identity is not a function we have anymore. Loads an identity matrix. Okay, so think of a 4x4 identity matrix, that's what gets loaded. GL ortho is still a function that is effectively in use today. We will be talking a decent amount about it. For now, imagine that we're setting up a three-dimensional viewing frustum that is from 0 to 100 in the x and the y dimensions, and from -1 to 1 in the z dimension. That's what that function is effectively doing. Another way to think about what that function is doing is it's specifying what are the valid range for the vertices that you're going to then specify that one can expect to show up on your screen. In other contexts, because we don't have any of that vertex transformation hardware yet in place, we've limited ourselves to vertices that are specified in these so-called normalized device coordinates. And we'll be talking about that eventually as well, where to get something to show up on your screen, it had best stay in that -1 to 1 range for your x and your y. And you can try that. You can try that on the lab infrastructure. You can try that with the OpenGL programs. Specify an x value of 7 and see what happens with that particular primitive you're generating. But if we separately specify beyond the defaults of saying, okay, my viewing region is going to assume valid x values from 0 to 100 and valid y values of 0 to 100 as well, that allows us to then specify our vertices in something a little bit closer to like a pixel space or like a screen space on our screen. One approach isn't better or worse than the other. It's really a matter of, what is the easiest way for you to represent your geometry in a scene. In this case, that's how this example is set up. So anything from 0 to 100 is valid. So we can imagine with 0, 0 being the upper left-hand corner of our screen and 100 being the lower right-hand corner of our screen, that you could then roughly specify your vertices in effectively what is like a screen space there. You're basically specifying not these values from -1 to 1, but effectively pixel locations directly. We could do that in our hardware, but we would then need to have a piece of hardware in place that we don't yet have that would take care of this transformation for us. So this code would work on your workstation, would not work on your hardware yet. So if we do so, we can look at the old school OpenGL and kind of squint and I think guess what's happening here. So GL begin, GL end is the old school way of specifying what is now just specified in a vertex buffer object. After or in between what the begin and the end call, here are all the attributes for the ensuing vertices that we want to specify. It's the old way of doing it. I think you can also see why it's kind of inefficient as well. Just lots and lots of function calls for every different vertex that we want to specify here. All of those function calls are in the API. They all have that driver overhead. They all potentially require some sort of explicit handshaking with hardware each time we want to call it. You can maybe, although for maybe, 4 vertices, not see too much of a difference. If we want to specify 400 vertices this way, you can see how efficient that would potentially be, right? Just all those function calls. Whereas in modern OpenGL, we just set up the buffer, set up that buffer array object, and just draw that buffer. And so it's roughly 3 function calls today, no matter how many vertices we want to specify. Let's try to squint and look at this and try to figure out what's going on here in our best estimation. There's a call to GL color 3F, which is also old school. We're setting the state of all future vertices are going to have this color attribute associated with them. 0 for red, 0.5 for green, 0 for blue. We're specifying, until we change the state, expect green vertices coming in. Then there's a call to GL vertex 2i. Back in this era, as opposed to having more of like an object-oriented approach, each of the function calls had that little suffix associated with them that would specify, in the beginning, would specify the functionality, and in the end would specify what variant of that function call you actually were expecting. So you can interpret this as everything is GL, that's still the case today, everything is OpenGL. The actual API call is just called vertex, so I'm specifying a vertex. 2i, there's two parameters, and they're both integer values, and that's why it's GL vertex 2i. And you can see and imagine for that reason why the API books are so large, because there's lots of permutations of that class of function that you'd want to be able to support. So we specify first the color, 3f, 3 floats, GL vertex 2i at 1131, GL vertex 2i at 3771, then GL color 3f of now a red vertex, followed by two more GL vertex 2i calls afterwards. What kind of object, what kind of geometry is this going to look like when it gets rendered on the screen? Can we squint and kind of see it? That's the best possible answer, I think. A trapezoid kind of thing. I think trapezoid. It's a quadrilateral. Yeah, it's gonna be a trapezoid, right? Because you're specifying a line and then two more lines. A greenish-red trapezoid, I guess, would be the best way to describe what we would have for this kind of object. I could have run it, but I just screenshotted it and provided it this way as well. Maybe now, after the fact, we can look at it and see more clearly, although we haven't talked explicitly how GL triangle strips work. I know in the lab you've had to kind of figure that out yourselves and understand what's happening there. But if we just go back to how things are getting specified here, white background, pixel values from 0 to 100 in the x and y dimension. I can't reach all the way up there, but assuming that this is 100, 100 in the xy dimension here, sometimes we get it backwards. If everything's flipped upside down, you know what bug you may have in your viewport or other hardware. We specify, starting with green vertices, we are going to have 11, 31, 37, 71. We then switch to red. We have 91, 38, 65, 71. We wind up with basically specifying our first triangle that's 2 green vertices and 1 red vertex, and you can kind of see the gradient that gets formed in that way. We then specify 1 additional vertex, and that allows us then to give us that second triangle there. That's the GL triangle strip object here. What happened to these vertices as they go down the pipeline? Some of this is happening potentially on the driver side. This is something that OpenGL as a spec doesn't say where these things have to happen. We have to make our best guess based on existing implementations and open source software for where these things happen. But it's some combination of software on the driver side and hardware in your actual pipeline. The first thing that's going to happen is the so-called vertex assembly stage. This is different than primitive assembly. We're going to talk about that as well. Vertex assembly is an attempt then to take these inputs that could be provided in a whole bunch of different formats with differing amounts of information associated with them. Just to give an example, here we're specifying via calls to GL color 3f followed by GL vertex 2i. That is the fixed function API calls, and I still like them because I think they're easier to kind of read through than all the buffer code we have now. But even if we're doing it via vertex buffer objects, we're still doing effectively exactly that. We're specifying amount of data, like a dimensionality as well as a length of our data, and we're also specifying to some extent what format that data is at the API call. This could have been GL color 3i. This could have been GL vertex 4f. There's variants of that in terms of how that data is getting specified. They're all doing roughly the same thing, but that first stage then is in either our driver as well as in our hardware, is to take that input, which could be in all sorts of different formats, and to force it to one predefined canonical format where we're just saying, no matter how you specified your vertex, from here on out, this is the format that the vertex is going to be. OpenGL specifies some potential parameters for what that canonical format needs to be, but doesn't actually say your implementation must use 32-bit floating point values for this particular data type. It is kind of our decision how we choose to represent our things internally. And again, internally here could be from the driver side, it could also be from the hardware side, and that requires us to do two things. One is to do just blatant kind of like data type conversion. So if stuff was specified as integers, we need to convert it to whatever our hardware is going to need it to be eventually. Or if it's specified as full, so, IEEE 754 floats, maybe we don't want to do that in our hardware, and for our design decision is we're converting it to that Q16.16 fixed point representation. We also then have to kind of fill in what may be missing. If we specified our vertices as GL vertex 2i or 2f, we specify just an xy, because we're not doing anything with z yet in our hardware, right? So we're specifying everything in just our xy plane here. Internally, canonically, either at the driver or at our first stage of hardware, we have to convert it to that internal format that the rest of our pipeline is going to expect. So for example, we would then have to, if we just specified our xy, we specified everything as a 2 vector, internally we would then have to convert it at that assembly stage, at the vertex assembly stage, to then have the other unspecified values at the very least. Z information, W information. For color, we would then have to potentially specify our alpha, our transparency information, if we didn't already specify it. So for that simple example, if you want to think of it in terms of like software data structures, our input would have been to this stage pairs of integers for position and 3 floats for 3 normalized floats for our color information. Our output would be these 4 vectors. It could be vectors, it could just be structured data here, where we've then filled in what otherwise wasn't already specified. So we're going to fill in, if it's not otherwise specified, 0 for Z and 1 for W, and 1 for alpha if we didn't otherwise specify anything for alpha here. And then potentially also some changed internal data type representation as well. For our purposes, we do that conversion. We just don't want to have to build out any floating point hardware. So we convert everything to that 16.16 16 point representation. We do that entirely in the driver, the conversion, but then our vertex fetch module is actually responsible for effectively padding the values that we have here as well. So that is the vertex assembly. We call the unit vertex fetch in your graphics pipeline module in your simple graphics processor. It could have been called vertex assembly as well. It's doing the same thing. In our cases, it's doing both, right? We're specifying these buffer objects. So that module is basically doing large DMA transactions. Give me the next buffer that I've specified. Give me all that data, and then do some of that internal conversion to this canonical format. The driver, in our case, this is just in our implementation, does all of this where it does that conversion to Q16.16, but to make sure all of our data is very regular, our hardware is making sure that no matter what, we have our X, Y, Z, W, and our RGBA for the attributes that we're specifying. We actually also assemble the other 2 attributes, even if those are also completely unspecified as well, such that, although it's not being shown here, we have not just 2 of our 4 vector fixties, we always are going to have 4 attributes per vertex. We're not using the other 2 right now, and OpenGL does require that we support more than 4, but that's what our hardware supports right now, 4 different attributes. That makes those hardware, if you look at the vertex fetch module, makes it a little bit more straightforward in that you don't really need to build a software engine for it. You can just have 4 FIFO queues, and you just assemble your vertices by just reading from those 4 queues. If one of the queues is empty and there's no data for it, you just fill it with nothing, and that gives you this canonical format for our internal representation here. That is the first stage, that's vertex assembly. I think that's all I have to say about it. It's kind of done for you, but you should now, when you look at the driver code that is handling the calls to GL draw arrays or setting up the vertex buffers, as well as this module itself, the vertex fetch module, now you can look at it from this context. That's what it's trying to do. Not just grab the data, convert it all so that going forward, it's all in the same format for the rest of the stages of our pipeline. The next stage would typically be vertex transformation. Again, this affine transformation where your lines are preserved and your amount of parallelism is preserved in your primitives here. It is effectively a 4x4 matrix vector multiplication, although in programmable shaders you can do all sorts of other things with that stage as well. You can convert lighting and texture coordinates and things of that nature. We don't have that hardware, but it's coming soon. We're going to be able to cover the concept first before you really dive into the hardware for that. For that simple example of the trapezoidal looking red-green thing, there is a series of vertex transformations that are happening. We had that call to that function called GL-ortho. So we're setting up that we want all of our geometry to fit into that 0 by 100 or 100 by 100 box. We then have to take our input coordinates and we have to scale it to that box. So that does require, via the GL-ortho call, setting up a particular 4x4 matrix, taking every one of those vertices as they come in, and multiplying those x, y, z coordinates by that matrix that gets set up in that call. There's a lot of algebra underneath the hood of how that happens. We will talk about that eventually, but that does happen in this example. For your current MP2 software that you're running, we are avoiding any of that. So there are no calls to set up the matrix. The shader is the pass-through shader that just copies input to output. So for you right now, your vertex transformation is doing effectively nothing, right? And so we can actually skip the hardware entirely without any loss of correctness between what our workstation is printing out or displaying in our window and what you're seeing on the attached monitor. But we'll get there. That, soon after this lab is done, you'll be able to get that working as well. By the way, any red triangles on the screens as of yet? Tomorrow. I'll stop by tomorrow and I'm expecting to see lots of really fun red triangles. So we'll see how much you already know this topic by having to do it in the lab already. That next stage, after we've taken our vertices and we've potentially applied that matrix to them, we've moved them around, we've taken our trapezoid, we've potentially stretched it and moved it in various directions, still maintaining its original type of shape via the affine transformation. After we do that, now we're at the stage where we can stop thinking of it as individual vertices in isolation, but instead now think of the actual polygon geometry that we want to continue with our render. That assembly now is referring to primitives, and in primitives we're talking about either points, lines, or some type of polygon. Other places you will just use the term primitive to refer to triangles directly or polygons directly. That's also generally fine for our assumptions. In terms of the data structure we're getting back out, one way you can now think of it as, before we had that vertex structure that had the attributes, had the x, y, z, w, had the RGBA, and now there's this other module, and this would be a piece of fixed function hardware that you're currently building out that would take a certain number of those vertices and logically group them together into one primitive type. So if it's a triangle, you can think of it as every 3 vertices that we receive, we're going to group them logically together, call that end result a triangle here. And that should be the output of this internal module that you're currently building as part of your MP2 as a team. It's not that straightforward. We'll talk a little bit more about what that means in practice, but that's kind of the end result of it. We specified a certain number of vertices, and for the triangle strip, it's a little bit trickier than if we had just specified it as triangles, but we specified a certain number of vertices. At some point, we have 4 of these vertices coming down the pipeline, being processed sequentially on a one-by-one basis here, and then there's this module whose task is to determine, first up, what the primitive type may happen to be. Based on what the primitive type happens to be, take, for example, the first 3 vertices that are specified and output a triangle. And the triangle itself then really doesn't have any additional data associated with it. Perhaps, depending on your rasterization algorithm, you may need to specify, for these vertices, how many of them are valid. But if we assume we're rasterizing just triangles in our hardware, you really aren't specifying anything else at all in terms of data here. This module takes 0, 1, 2, collates them together, considers that one object, and sends it the rest of the way down the pipeline. Then, because it's a triangle strip, we actually preserve the last 2 vertices that were specified, wait for one additional vertex, then combine those three together as a new triangle, send that down the pipeline. This example just has the 4 vertices, but if there was a 5th one over here, we would take 2, 3, and index number 4 for the 5th one here, and we would specify that as an additional triangle to send down the pipeline. That's what your primitive assembly is doing. Given a set of vertices as they come through, handle them on a one-by-one kind of sequential pipeline basis here, based on the current primitive that you are specifying. Emit polygons. Emit further geometry for the next stage. There are all sorts of polygons one can specify conceptually. We could specify self-intersecting polygons like this bow tie example that we would have here. We could very easily, given more than 3 points in our space, specify so-called concave polygons. A concave polygon is just a polygon for which, for any arbitrary 2 points inside our polygon, we could draw a line between them. If the line between them can ever potentially pass outside of the polygon, then it's concave. Otherwise, it's defined as a convex polygon here. There are algorithms to do things like that, both to rasterize concave polygons, as well as polygons that are self-intersecting, as well as polygons that have holes in the interior to them. There are all sorts of algorithms, and there are books written on the subject. For more traditional kind of 2D CAD rendering, there's a reason we would want to be able to support that. In 3D rendering in modern hardware, the use of those algorithms is not nearly as common. This is, having just said that, slowly changing. If you read up on tessellation shaders, and we don't really cover them in this course, the idea there is you're specifying a relatively small amount of geometry, and you're telling this other additional programmable shader stage to say, given this relatively small amount of geometry, reinterpret it as a much more complex piece of geometry. That's effectively what it's doing. Instead of a square made out, this is really oversimplifying, but instead of a square made out of these 2 triangles, instead interpret this square as being made out of 8 triangles or 64 triangles to give more potential dynamic level of detail. That involves then rasterization of more advanced shapes depending on what you're specifying for your tessellation shader. But for the most part, we don't really lose that much generality by limiting ourselves to relatively straightforward convex polygons. Polygons for which you can't draw any line between any 2 points and have it be outside the polygon shape itself. So no algorithms to specify rasterization of a star shape or of a bow tie shape. We haven't talked much about the project for this course, but as we get through our MP assignments, you'll have that last kind of 4 to 5 week span at the end of the semester where you get to set your own MP assignment, basically, is how I'd want you to scope it. And that's a potential idea. You could build a tessellation shader. It's something we should be able to support in our hardware. As long as you scope it appropriately, that's just one potential project idea. As you're working on the lab, one way to think about project ideas would be if you ever have a question that comes up or a comment that someone in your team makes where they say, boy, it's really frustrating, or wouldn't it be nicer if our hardware could also do this? And if whatever that this is a reasonably well-scoped idea that could be implemented in 3 or 4 or no more than 5 weeks as your team, then that could potentially be a good project idea. We can wait a little while before we get into project ideas, but it has to be something kind of tractable for a team that I'm not providing you a lab assignment for, right? You're determining effectively what your own lab assignment is going to be for your project at the end of this semester. This is just one of many, many possible examples of what you could do for a project. Rasterization of things other than the MP2 rasterizer is a perfectly valid project idea. So polygon triangle equivalents. For the most part, our assumptions can be all polygons or triangles, or perhaps should be. Triangles are always going to be convex, and that definitely limits the amount of special cases of what our rasterizer has to handle. And it simplifies the type of algorithms we can apply for rasterizations. There are still those other types. There's the GL points type. There's also the various line types we also need to support. Some systems actually treat those as just a special type of triangle. Alternately, you'd have basically a separate branch in your hardware given the GL primitive type. If it's a point, basically just pass it on. Maybe deal with point size and other things for rasterization. If it's a line, we'll talk about some of the line algorithms. But now if it's any of the other types, treat them as triangles and apply these triangle rasterization algorithms for them. Because we have just 3 points, and 3 points allows us to define a plane, all of our triangles are guaranteed to be on a single plane. And so all of our rasterization algorithms, which as we'll see conceptually aren't really that complicated, can be extended directly to triangles without any loss of correctness or generalization. So that's more of a normative claim than an actual factual claim, but we can get very far with our understanding of modern graphics hardware by limiting ourselves to triangles, either by requiring that our geometry shading and or primitive assembly stages take everything we specify and return triangles, or just by self-limiting ourselves to saying, we're going to break everything we have down to triangles and learn how to do that rasterization of triangles. You can design really complicated, crazy scenes just by limiting yourselves to your polygon types being limited to that of triangles. And I know we've done a little bit of this in the lab already, but I want to make sure everybody is roughly on the same page. So I wanted us to take a few minutes, and we can kind of collect results, or you can kind of just internalize it as a group. And I want to make sure everyone's on the same page with regards to what you need to do for your primitive assembly here. In your hardware, if you look at the NP2 document, I did mention that you can generally ignore the line types for now, that just assume that they're not going to work as you specify them. So yours was expected to handle GL points, as well as all the other triangle-related types. I'd like you to take a couple minutes and move around the class if you need to go back to your team, if they are here, and walk through. You can think of it in terms of a state machine, as always. You can think of it in terms of a software algorithm. If a data flow kind of view of what you're doing is how you like to think about it, all of those can be made equivalent to each other. Let's take about 3 minutes, and I want you to walk through with your team how you would handle, for now, GL triangles, GL triangle strip, and GL triangle fan. Input to this module, just make sure we're all on the same page, is a sequential stream of vertices. And just call it vertex. We know what that data type entails, both conceptually as well as it does what it means in our hardware. That's our one input, is a stream of those. Our other input is there has to be some sort of state that we're still specifying via our GL draw calls. GL begin and the fixed function OpenGL. Somebody has to tell this module what the actual primitive type is. So that is an input here. There's going to be some case switch statement corresponding to the input. The other thing, which fixed function OpenGL makes actually quite a bit easier to handle than our current buffer-based OpenGL, there has to be some sort of end input as well. Some sort of way of specifying, I'm done with that type of primitive for now. Let's take about 3 minutes. Go move over, walk over to your team. And if your teammate says, oh, I already know exactly how to do that, then have them explain to you how they did that, how they accomplished that. That's great.
Basically, it's got a state that grabs vertices, and it's just kind of, there are 3 states. Grab the vertex 0, grab the vertex 1, grab the vertex 2. Each one. And once I have 3 of them, it checks what type it wants. So I just want a triangle, and then you have this. If it wants triangle strip, it outputs those 3 and then jumps back. First it outputs the 3, reorders them so that.
So for like the GL triangle strips, yeah, you read those for value of text 1, right? And then you go back to the second vertex because you've already read the 0
jumps back to
and V1 and V2
grab
are
the
shift
last vertex.
to the vertex over V1. Right, you're gonna read in V3.
Information so that I'm
And
still
then you have
storing
another
the
two
two
vertexes, you write it. And then you
Grab
that.
each vertex.
So the cycle pen,
Yes, so
Grab
it's the same thing, giving you
one, and then you just jump out.
back to
Getting
the
it
right.
yes,
And then-
so that
This time, like the first vertex, you're just gonna stay the
grab the
same.
last one and then go right
You're
back
gonna
to
shift
the
vertex two. Alright, so vertex.
You have 0, 1, 2 as vertices.
You're gonna shift V.
Let's say it's a strip.
Vertex
So you're gonna get
one. And then you're gonna
You make 1 and 2, 0 and 1.
And then, yeah, you're trying that.
yes, so that two
You're
is
gonna
not
just
just
write
right,
and you're gonna
the
get
vertex, the first vertex given, right?
So the interesting thing I want to say for this, that example,
And keep doing that until you get
7 and 2.
the GL ends is
So
until
we
I
have
have
specified again,
last.
is it even with the vertex, or do we have to like say 2 and then? Yeah.
That, I have an output from the box, curve assembly, so I can.
Yes, sir.
This is the
So
last
in
triangle.
the triangle fan example,
It's tricky.
yeah, so when you get towards the end, when you're reading 1, 2, and 7, or we're reading 2 again, is that something that could be like provided again, or do we have to save it somewhere?
And so what you will see is that, you don't do that correctly. Is basically there's an unspecified triangle in your triangle fan. It'll still look okay, right? You'll just have one missing triangle, and depending on the size of your fan, you may not even notice that it's missing, right?
Right.
But yes, there's kind of a hidden triangle at the end of your triangle fan, which is kind of fun. All right, that's a good question. That's a sign you're asking the right questions at least here. You guys can stay where you're sitting now unless you need to go back to your computer and take copious notes. Otherwise, stay where you are now. Of those three, triangles is probably the easiest, right? When I'm specifying GL triangles, there's really not a ton of state that I have to keep track of. First off, let me ask a hardware question. This will be a sign who's been elbow deep in Vivado, as of course they should be. I've built this module called Primitive Assembler. How do I know that I've got a valid vertex coming in? What signal do I need to monitor? What's the bus interface that would be coming in on? T-valid, that's right, because it's an axis stream interface. It took me a second, but I caught what you said. Axis stream, and that's an intentional design decision. It didn't have to be implemented that way. Basically a buffer interface on both ends of this thing here, right? So monitor T-valid, which is just the valid data on my axis stream. Every time that cycle's high, and I have that T-valid, T-ready kind of mini handshake there, I know I've got a valid vertex coming in. If I know my primitive type is GL triangles, what does this state machine have to do?
Grab 3 vertexes.
It's got to count to 3, basically. Yeah, right? It's got, and I would keep it as really simple as possible. Grab vertex V0 state, then go to grab vertex V1 state, then grab the vertex V2 state. Technically, you could output that triangle right away, go to another state that says output triangle, and then actually do that handshake. Because just like we have to monitor T-valid here, we also have to monitor T-ready here, right? That even if we are ready to output a new triangle, maybe downstream, I always get my upstream and downstream backwards. I'm going to call that downstream. Maybe it's not ready. Maybe it's in the middle of rasterization. It can't handle, it's doing triangle setup or actually rasterizing the previous triangle. It may not be ready yet. So grab all 3, wait until you can actually send it, then send it out. That is my GL triangles rasterization algorithm. Not really an algorithm. Definitely a good place to get started, right? If the rest of your team is really ready to get rasterization working, you tell them, hey, I have a primitive assembly module. It only works for GL triangles, but you can test a whole lot of things with just your GL triangles, and you're in pretty good shape there. This OpenGL primitive type also then has to be specified some way. Does anyone tell me how that gets specified in our system? Sure. It's it is a type.
Like 1 to 7 or.
Someone has to specify who.
Oh, yeah, right.
The driver, at least in our implementation, is how the driver does it, right? The driver does it. We have a GL draw arrays call. as part of that GL draw arrays call, you look at that function call, it does specify the primitive type. I think it's the last argument, but it's one of the arguments to GL draw arrays. That probably is going to be an AXI-Lite accessible register in your rasterizer component, and your driver then has to actually set that. That doesn't get set for you. You have to actually do that yourselves. Double check that that actually happened. If you're testing your hardware and just no triangles are happening, you should have some maybe good default case or something like that. But if nothing else, confirm that you're actually getting the value you think you are getting. Make sure that your driver's actually setting that value. So for GL triangles, we're pretty good to go. What needs to do different for GL triangle strip? It's pretty similar, but what needs to do differently? And I don't know how well you can see the numbers that are listed there, but they're intentional, right? V0, V1, V2. I can grab this from an arbitrary resource somewhere. Yeah, sure.
So you have to shift the register values and then be able to read the most recent or newest verses that's coming.
Another way to say that, for your first three vertices, it's the same basically, right? You haven't done really anything different. V0, V1, V2, we got a triangle. So for the first triangle of our triangle strip, your assembler is working effectively the same way. But look at what's happening now here. By the way, there is a little bit of an issue with regards to the ordering of these vertices in our triangle. If you do it wrong, I think your results are still going to look pretty good. But one thing that we will learn relatively soon here, it's kind of hidden in our rasterization algorithm already, is that generally we care quite a bit about the orientation of these triangles. And generally, we have to specify whether they're forward-facing or front-facing or back-facing. One way we specify that is by the orientation, whether the vertices are in clockwise order or in counterclockwise order. And so what I'm going to tell you here is going to be a little bit annoying. But if you get it wrong, you may still get a pretty good-looking triangle strip here. V0, V1, V2. We've sent out our first triangle. We have to have some mechanism. You can think of it like a stack. I wouldn't overthink it in your implementation. Just another register to hold those last two vertices somewhere. V1 old, V2 old, whatever you want to call them. Previously stored prior to vertices have to go somewhere in your design. You have a little memory module, you can have a stack, or you can just have a register that for V0 we know it's kind of a one-time thing and we're done with it. We've grabbed V1, V2, that now maybe becomes V0 old and V1 old or something like that, so you've kept track of it. Because now we've received one more additional vertice, and now you can specify a triangle with just that one additional new vertice plus the prior two vertices here. So, I don't know how much I want to belabor this point. V0, V1, V2, is that clockwise or counterclockwise, that triangle? I don't know a better way than just kind of like draw like a little finger around the triangle. Which one is it? It's clockwise, and I don't know, just as you kind of trace through it. V1, V2, V3 is what? Yeah, so technically, what your primitive assembly should be emitting should be some combination of V3, V2, V1, or V1, V3, V2 to get a same orientation triangle as what the first triangle in your triangle strip is. I do believe for your rasterization implementation will be okay either way, but technically you need to keep the orientation of every triangle in your triangle strip. But no matter what, the concept of like storing the previous two vertices and then combining that with the new one that comes in is what your rasterizer, is what your primitive assembler needs to do. I would argue that for everything other than GL triangles here, this end signal is pretty critical to your primitive assembler, so don't forget about it. The issue really becomes, how do I know I've ended one triangle strip or fan and have begun a new one? In old fixed function OpenGL, we had this really nice call to GL end, and that was basically our way of specifying, I'm now done with this primitive. There may be another primitive coming, but this primitive at least is done, or this primitive type is currently done. We don't have a call to GL end. What do we have though? Do we know? What can we use? Yeah, we have that kind of user-defined signal in the AXI stream that our vertex fetch module is using for us. Vertex fetch is the only module, at least how it's designed right now, that knows how big that GL draw arrays call was. Your buffers can be of arbitrary size within some reason. GL draw arrays doesn't have to draw the whole buffer. I think that's normally how we set up our open GL call, that if we have 30 vertices in our buffer, we do GL draw arrays with all 30 vertices. That's generally how we do it, but it's not a requirement that be the case. As part of GL draw arrays, one of the things we specify is, for the buffer we have, here's how many of those vertices we're actually wanting to draw at any one given time. The GL, the vertex fetch hardware is keeping track of that. It was told, fetch 30 vertices, or however many. It's got its own just a little counter, keeping track of how many it's already fetched, how many it's already spit back out. When it gets to the 30th, when it gets to the last one, it sets in this axis stream that value of T last, which if you look at the axis stream spec, that's all T last means. It means this is the last data point for now. It doesn't really say much. It doesn't really mean very much. It's up to us as we implement the hardware that's axis stream compatible to kind of interpret that how we see fit for our own purposes. But that's what that vertex fetch module is interpreting as. You better monitor that signal. So that's how you know that you're done with the current primitive type. That's how you know you can kind of stop queuing up the prior two vertices. We've sent our last triangle, we just go back to state V0, or wait for first vertex, or wait for begin, whatever you want to call that state in your state machine. Now, that's T last from the primitive assembler perspective. You may also then want to forward T last down the line as, this is my last triangle, but that's a little tricky as well, because from our rasterizer's perspective, it doesn't really care if it's the first triangle, the second triangle, or the last triangle. Your rasterizer should itself be setting T last to say, this was the last fragment in the current triangle, because we may want to know that information to know it's time to expect the next triangle, and that's how we know that we are done here. That's triangle strip. Triangle fan is a little tricky, and that's why this team asked a good question. At first blush, it looks kind of similar. We specify our hub and spoke kind of geometry here. We have our first point, and here it's not labeled the same, but this is our very first point here. We then specify for two more vertices, that's our first triangle. And now for every additional vertex we specify, we're not keeping the last two vertices, but we're keeping that initial vertex as well as the most recent one, and then with the new one, we're combining that together to make the new triangle that we're generating. My only recommendation as you build out the state machines for these is, I just don't think you should try to be too clever. That's just my opinion, that have a state machine for triangle fan and have a state machine for triangle strip. Technically, they have a lot of states that could be in common, but the trade-off is I've saved like 2 bits in a flip-flop somewhere for my state machine, and I've made it a lot harder to debug and test. The design choice is yours, but that's just my opinion of, just keep it separate, keep it simple. Because as someone was asking at the very end, there's kind of a hidden triangle in our triangle fans here, right? So for triangle strips, nothing's really hidden. After our first 3, every vertex that comes in is specifying a new triangle. We just got to keep track of the prior 2 to generate those triangles. Triangle fan looks pretty similar. Instead of keeping track of the last 2 vertices, we're keeping track of that initial vertex as well as then the most recent vertex to generate our new triangle. We do 1, 2, 3, 4, 5, 6. We specify 7. That's a triangle with 1, 6, and 7 here. And then we get our GL end, or our T last call. And what we see there is a triangle that's not specified at all. We don't actually specify this point 2 again. There is no second point 2. That is just the second vertex that has come in through here. So when we specify GLN, or T last buffer entry, it's going to be this vertex. And so your state machine needs to remember, oh, that means that there's one final closing up the fan triangle, which is not just the first vertex, it's also keeping track of that second vertex with the most recent vertex, and that gives us our last triangle here. You don't need a triangle fan to specify a hexagon, right? I mean, you can, but you don't really need it. You need triangles for more complex kind of geometry that you want to specify. And when you have more complex geometry where there's 100 points in my fan, and you're missing one triangle, you're probably not going to see it. So if you don't get that working, it's also not the end of the world. It's going to be like a missing kind of sliver here. There hasn't been a ton of excitement about like the bonus point criteria for these labs. Maybe everyone feels very comfortable with the grade they're getting in this class, but the bonus points are supposed to be nice, you know? Hey, I got the bonus points on MP1, I can kind of, you know, take it easy on MP2 or not stress out about it as much. The bonus points for MP2 is a little tricky in terms of how I specified it. I'd like to kind of refactor the bonus points right now and say, for that one example that uses triangle fans and strips, if you can get that one to fully work, that'll be the bonus points for MP2. That's the color wheel example, and you should be able to, but everything's got to be, you know, right on point in terms of assembly, in terms of rasterization, and you may have to port an old fix or two for MP1 to get that example to work perfectly for MP2 here. Questions about primitive assembly? It's one of those things that doesn't seem to work conceptually. Of course, building out the state machine and thoroughly testing it is not necessarily that straightforward. You can get pretty far in MP2 by just sending triangles down. If that's the part that you're finding very frustrating and stressful, just work with triangles, only do those triangle kind of applications for now, and then once you're really confident in your rasterizer, then worry about this other stuff that you also have to support. Which leads us to rasterization, which is obviously how you're spending your time probably tomorrow in lab. The idea behind rasterizing, although the etymology of the term doesn't really necessarily make that clear, is to determine which pixels or potential pixels should be turned on and with what attributes corresponding to those values inside a primitive. We're going to generate a potential pixel. In fact, that phrasing there is a little wrong. We're going to generate a fragment for each location inside our triangles and assign also whatever other attributes are associated with it here. We tend to focus on color because color is easy to kind of visualize and see. But we're going to determine for all the attributes we specify for our vertices what the corresponding attribute values should be for all of those locations inside our lines, our points, or our triangles that we have specified here. Again, it's easy to visualize this is green and this is red, so we have to specify our gradient here. Which pixels should potentially be turned on? What should the values of their attributes potentially be? But in fact, color is just one of the potential attributes here. This is showing kind of a two-dimensional view of what it would look like on a screen, but there's also going to be that depth information, that Z information, that third dimension associated with each of our vertices that we specify. We also need to do that interpolation, that rasterization for those attributes as well. There could be other coordinate information as well, texture coordinates that you don't see at all when you're looking at that here, but we specify them for each of our individual vertices. We then also need to do that kind of gradient calculation, that interpolation for all of those values here. And in fact, and I don't know if this makes the hardware as you design it easier to understand or less easy to understand, the actual positional information is also what's getting interpolated here as well. It's just on a discrete grid, so it doesn't really look like it's interpolation. But if this was a value of, what was the x, like 11 here, and this was 73 or something like that, right? We're also actually interpolating that xy location information as well. The difference being, though, the limitation or the restriction there being, is that here we're rasterizing to effectively a screen, right? To screen coordinates. And so we generally, for now, only care about the locations in x and y that correspond to the values on a grid. So if we have 11 for x for the first vertex and 73 for x for the second vertex, we generally only care about 12, 13, 14, 15, 16. We don't need to until we want to do some subpixel anti-aliasing calculations. We don't need to care about 11.25 or something like that. And because we can generally do our rasterization under that assumption of it's connected to a screen, we care about pixel 11, then pixel 12, then pixel 13, then pixel 14. Because that's what we can restrict our caring about that attribute for, that actually can kind of simplify the amount of hardware that is going to be required at the end of the day. Otherwise, it involves a little bit of calculus, right? It's sort of a two-dimensional gradient that we're calculating here, and we have to determine how that value should change across that gradient. But in practice, it's this discrete grid. And while we do have x, y values that are changing as we go across our grid, if we limit ourselves to them changing by plus or minus 1 as we go, that actually kind of limits the amount of math that's going to be required. And we can kind of basically fool the hardware into doing the rasterization without doing very much math at all. That maybe was a more important design criteria kind of in the early days of GPUs, in which every multiplier was critical, every divider was a really fundamental design consideration. So when you look at some of these algorithms, and we'll start with lines and work our way towards triangles here, I want you to keep that in mind. And that's still relevant for our design purposes as well, which is, yes, I know how to design something that has 200 multipliers in it, but my FPGA board, which is all our instructor could afford, is very limited in terms of how many multipliers we can actually fit on it. So those kind of like old school techniques that were really meant to minimize the hardware required, still pretty relevant for us because we have this limited resource we're kind of targeting here. Let's talk about rasterization. I want you to think of it in two terms here. First off, and I want you to kind of convince yourself they're equivalent, I want you to think of rasterization as what pixels or what fragments should be inside my triangle or on my line, as I'm going to show in this example as we do Breshan-Hans algorithm. What squares should be on or off, if you want to think of it that way, inside my triangle. That is rasterization's goal. It is also what should the attributes of these things be that are inside or outside my triangle. How green, how red, greenish red should it be as it goes. Rasterization is doing both of those things for us, but they're actually equivalent computations that we're doing. They're both determining the attributes for these fragments inside my triangle, for which position x, y are just two of those attributes. R and G are just two other attributes that we're calculating here. So it's going to be relatively easy to visualize this first off in terms of, what are my x, y pixels that I'm turning on or off alongside my line. But it's the same thing, same exact math that we're doing for how red should those pixels be along my line. They are both a gradient. They're both just different ways of visualizing two different types of gradients. There's a gradient of green and of red as we go from this vertex to this vertex here. It gets less green and more red as it goes. But there's also a slope of the line in our XY location here. And it's the same thing, right? There's a slope of green, a slope of red, and then the actual slope of the position information here. So for our rasterization algorithm, we talk about Breshan-Hans line rendering algorithm here, very conventional, very famous kind of approach to doing rasterization. We think of it in terms of pixels being turned on or off because we have a slope of a line. But it's the same thing. There's a line that we just can't see here as easily. It's a green line as we go from left to right of how green it is. And then there's a red line as we go from left to right of how red it is at that location. So when I'm talking about slope, you can definitely think of it in terms of, Euclidean geometry and just calculating slope as rise over run. But we could have also done this as green channel to green channel here, which would also have a slope associated with it. We just use the term gradient. It's the same concept. How much our attribute changes as we go from one endpoint to the other is our gradient, is our slope here. Let's talk about rasterizing lines. How are we doing for time here today? We have time to get through most of this here today. We're going to do lines, and we're going to then apply it to triangles. And effectively, you'll see a derivation with a little bit less math than your pre-lab for MP2. So if we talk about lines, segment defined by the two vertices or the coordinate positions of our endpoints. In this case, we had just an arbitrary xy plane here. We have a point that's 2 in x, 2 in y, 7 in x, 5 in y. That's how we define our line segment, and we know we can take a ruler and we can connect those 2 points together and get our line here. But what happens in practice, right? That when we have some geometry we specified now as vertices using GL vertex 2i or our GL array buffers approach to drawing it, what happens when we actually try to represent that on a display? What happens? Well, our pixels and our display is ultimately sampling in that two-dimensional space, right? There's a finite resolution of our display, so there's a finite number of pixels, so that while we may have geometrically defined our line here, when we actually then sample from that line to actually be rendered on a display, we may find, if we are not careful, it may look something like that, or it may not look especially good. It becomes discretized, right, at some stage along the way. And rasterization is where it's going to happen for our implementation, where that we have the defined endpoints, but ultimately we have a series of pixels in this two-dimensional grid here, and while again it could be our gradient of green, gradient of red, but in terms of pixel location, either kind of on or off. We either have a pixel here or we don't have a pixel here. And likewise, even if you have a gradient of green, there's a finite amount of greens we can specify as well. So the same issue continues, that there's some sampling kind of issue here, but it's more easy to see when we're just looking at XY locations and those attributes. We have mathematically defined lines with endpoints. We ultimately have pixels that are some sample in that two-dimensional space that are either on or off at any given time. Rasterization, again, the goal of it is to determine what our attributes should be at those locations. What are the valid XY locations in our screen space, and what the attributes should be at those locations. Let's do some very basic math to make sure we're all on the same page here. One way to represent a line, has anyone seen and heard y equals mx plus b before? Everyone shake your head just briefly. That's, oh, come on. No, okay, I believe you. Y equals mx plus b, where m is our slope, and b is our y-intercept. That's the slope-intercept form of a line, where we define our slope as our rise over run, right? Our change in y divided by our change in b, and b, you can plug in any point once you have the slope on the line to get your y-intercept. That is where it is crossing that y-axis here. There's a point to this. Humor me for a second. Slope is defined by its start and its end coordinates, and you can have all sorts of different slopes for our line. Again, this is just thinking of our xy locations. All of our other attributes also have a slope associated with it. You define two vertices, two endpoints. You define the green channel for those two vertices. There'll be a green gradient between those two. A slope of green. How much did the green change from x0, y0 to x1, y1? And you can have all sorts of different slopes that you then are potentially rasterizing and determining the gradient values here. So this is all interpolation, but I think we can sort this out. Given this line, we can probably figure out that for every x-coordinate, what the corresponding y-coordinate would need to be. So given first point of 2, 2, second point of 7, 5, we can figure out for every valid x-coordinate what the corresponding y-coordinate would need to be. First, we would calculate the slope. What is the slope of this line? Say it again? 3/5, thank you, right? It goes up 3 and over 5, so the slope is 3/5. What is the y-intercept, the b value for this line then? Requires a little bit of math in your head. Y equals 3/5 x plus b. So 2 equals 6/5 plus b. So b equals 4/5, right? That would be our y-intercept of that line. So given the point slope form, slope-intercept form for an equation for a line, one way we could do this rasterization would just to be, we calculate that, we calculate m, we calculate b. We then take every value of x and we plug it into that equation. And if you were in, fourth grade or something, and you were asked to draw something on a, sheet of graph paper, that's some type of approach you would basically take for it, right? I don't have. Let's see if I can get the little pencil here, right? So we'll do this the best we can. We know we have. Oops, 1 second. We know we have 2, 2. It's going to be red. And we know our other point was 7, 5. Yeah, it looks great. And we know our equation is y equals 3/5 x plus 4/5. So for every possible x we were interested in determining here, we would just plug it into the equation. Y equals 3/5 x plus 4/5. We plug in a value of 3. Plug in a value of 3, we get 9/5 plus 4/5, 13/5. We get 13 over 5. we then have to determine what pixel that corresponds to. So for x value of 3, y equals 13 over 5. I want to make sure I actually get the math here right. 13 over 5, I did do that correctly. That's 2 3/5. One potential approach, although there's no saying that this has to be the way, is we would just round it at that point. We get 13 over 5, 2 3/5 for our value of y. We would then round that up to 3, and we continue. For x value of 4, that's 12/5 plus 4/5, that's 16/5. See if that's correct. 3 1/5, yep, my math is still fine here. We round that down to 3. So this line's not going to look great because of how I'm filling it in, but that's still, what that would be the pixel we would turn on there. We then check for our next value of x equals 5. We wind up getting 3 4/5. We round that up to 4. Finally, for x equals 6, we get y equals 4 2/5. That rounds down to 4. And we wind up with a line that looks something like this. Again, this is very much zoomed in our pixel grid. It's never going to look good that much zoomed in. But that's what our direct plugging into the slope-intercept form of our line equation gives us. It's not wrong. There's nothing wrong about this approach to rasterizing a line. Given two endpoints, we figure out the slope and the intercept. We then take every potential x value, plug it into the equation to get what that attribute should be at that corresponding x value. We do that for y, we do that for z, we do that for green, we do that for blue, we do that for red. We've then rasterized our entire line correspondingly. That's the example. We round the results to get our pixels to turn on. I guess I didn't need to draw it. It's pretty good. That's what our end result looks like there. And you kind of squint at it and you can kind of see, yeah, it's sort of line. None of these lines are going to look that good, but it's sort of line looking here. There's some downsides of that approach. Can we think of any? In terms of hardware, in terms of how we would implement this. It works. It's mathematically perfectly valid. There's nothing wrong at all with the approach mathematically. In terms of our implementation. I mean, we were able to figure it out, right? Little pencil and paper, kind of, I had to squint a little bit to remember how to calculate the slope and all that. We were able to do the math for it in our head. It's not that difficult. Pencil and paper, it's not that difficult. In terms of building hardware for it, there's a lot of extra hardware that this is going to require that you would then be responsible for building. We calculated the slope and it wasn't that bad. Take rise, divide by run, if you remember that. Delta y over delta x, calculate our slope. What does that require in terms of hardware? This is not meant to be a complicated question. It requires a multiplier, but it requires a divider at the very least, right? To calculate m, we need to divide. And in the certainly early days of VLSI and building graphics hardware, that was a big problem. And for us, it's a big problem because we want to avoid building a divider as long as possible this semester. Likewise, plugging in our values once we've gotten that equation requires multiplication each step. So even once we've done that division, we then have to do a separate multiplication for every single point along the way. That's a lot of multiplications just to rasterize that line. And then finally, even once we've done that multiplication, calculated y equals mx plus b for each value of x, we then need to do some rounding, which, depending on how we're representing the data, could itself also be a fairly expensive operation here. So this solution, if you want to think of it as such, is valid. It's fine. There's nothing mathematically at all wrong with it. It's just kind of overkill for both the hardware of early VLSI revolution days, as well as the hardware that we ourselves have access to for our Nexus Video FPGA boards. Just a quick note about slopes before we jump into Breshenham's algorithm. We use the more conventional representation of a line to calculate the slope of y as a function of x. There is nothing that requires us to do it that way. That is how you learn it in elementary school. That's how we think of, given x, we calculate y is a function of x. But that's kind of an artificial thing, right? There's nothing preventing us from calculating x as a function of y and consequently calculating our slope correspondingly as well. What if we had done it that way? What if for that example we had calculated the slope and not y as a function of x, but instead x as a function of y. Would the line have been any different? What do we think? Mathematically, arithmetically, exactly the same, right? It's still the same math. In terms of how we had to implement it there was one step that was going to wind up being a bit different potentially.
Would we be rounding the x values instead of the y values?
You would be rounding the x values. You'd be incrementing your y by 1 each step and then rounding the x value. Again, mathematically, that's still exactly the same, right? It's still the same line equation. You're still using the slope in effectively the same way, but based then on how our rounding would work, we would actually only have two other interior points of our line, right? We do y starts at 2, we would calculate x for y equals 3, we would calculate x for y equals 4, and we'd have although neither line looks all that good, we would have a not as good looking line as what the previous line would look like here. One thing then we can choose then to do is, without really losing any generality here, is to figure out which approach to take, y as a function of x or x as a function of y, depending on what the slope of the line is going to be. This is just a quick little aside, but this is going to be true for all of our attributes as well. Because just like we have the slope of the line, we're going to have the gradient of our green channel as well. And if it's very large in one dimension, we go from 0 green to a ton of green as we go from low x to big X. That's a very high slope. We may have then a relatively small slope as we go from smallest y to largest y value for that green channel here. So another way to think about that is we want these algorithms to generally work for a slope with an absolute value of less than or equal to 1. We get the lines that look pretty decent here. We had a slope of 3/5, it looked pretty good. If instead we have a slope of 5/3, which is what that alternate approach effectively gives us here, we can always reformulate the question and reformulate the line so that it is a slope of 3/5. So while we talk about Bressenham's algorithm here, you may realize that it really only works if the slope is less than 1. That is technically true. We can always reformulate our line so it has a slope of less than 1. If it has a slope of 4, we can just rewrite it as x as a function of y and wind up with a slope of 1/4. That's true of all of our attributes here, and so we can do just the exact opposite computation depending on what our slope actually winds up being. But we actually want to avoid calculating slopes at all. And we want to wind up avoiding doing any multiplication at all here beyond potentially some very initial setup here. One thing I want you to think about as we start to introduce this concept is that as we're assuming a slope between 0 and 1, as we go from an x value of x sub k to the next x value of x sub k plus 1, we're just moving 1 over in our pixel space here. We think of it as like mathematically a line we're trying to rasterize here. But ultimately, we're turning 1 of 2 pixels on. There's only 2, assuming our slope is less than 1, right? There's only 2 options for us. That no matter how that line is formulated, assuming a slope that's within that range, we're either turning on this pixel of y sub k, or we're turning on the pixel that's one above it, of y sub k plus 1. It's always going to be one of those 2 choices. And the quote-unquote correct choice, in terms of if we're using the slope-intercept form of the line, would be whichever one of those 2 choices is closer to the original line. Either way we're rounding, either way we're sampling in a 2-dimensional space, either way if we squint really closely on our lines they look kind of jagged until we do some anti-aliasing. But ultimately we're picking just one of those 2 choices. I'm going to leave this here for today because I want us to cover this properly on Thursday, but when we come on Thursday I want you to remember just that main point. Technically, yes, there's a mathematically correct value. We're only turning on one or the other. We don't really care what this value is. It's not relevant for us. What we really care about is which one is closer to what that value would be. And it turns out, this is the whole crux of Bressenham's line rasterization algorithm, it actually can be mathematically easier to calculate which of these 2 points is closer than it is to actually worry about calculating that line's value itself and to do all the rounding. Let's leave things here right now for today. hopefully I'm going to see some triangles on Wednesday when I stop by in the lab, but good luck on that, and I'll see everyone tomorrow, and then of course on Thursday.